Now that we've talked about units, let's talk about the numbers and what's really significant about them. There are two different types of numbers that we need to know and understand. They're called inexact and exact numbers. Because when we're making a measurement and the limitations of the device in which we're using, the number of values or place values that numbers occupy is important. Calculators typically will just shoot out as many digits as possible that they have the computing possibility for. However, when you are measuring with a device, the uncertainty or the limitation of that device must be accounted for in the number in which we are representing. Inexact numbers are obtained from said measuring device. It could be a balance, ruler, pipette, a volumetric pipette, graduated cylinder, stopwatch, anywhere where those base units we had talked about, the device we're using to measure those. The problem is with that device, it's going to contain uncertainty. When you look at a ruler, you would have what's called this uncertainty or this open space that is up for interpretation. So that area of uncertainty, if what we are measuring falls under this area, so we're going to measure this circle, it is going to be up to that interpreter to identify where that measurement falls, because we know it's more than 1 but less than 2. So 1 what? Therefore, we can only have our numbers, what we present, be as precise or as accurate as our measuring device can provide us. Accuracy is when we have a number that is close to what's called an accepted or true value. That means a value that the scientific community has agreed upon that is consistent. Examples can be the density of water at 4 degrees Celsius is 1.00. So again, that is something that, or that number is a true number. Precision is how close your recorded values are to each other. That is the reproducibility of the technique that you're using. So you don't necessarily have to be accurate to be precise or be precise to be accurate. High accuracy means you're going to have numbers as close to that accepted value. Precision means all your collected data are going to be closest to that accepted value. Exact numbers, there's no argument. They are exact. They are obtained by counting items or establishing equivalence. So we know that there are 1,000 meters in a kilometer. That's an exact number. We know there are in a pair of shoes, there's 2 shoes, that is that pair. So they are this set value that we don't need a measuring device to determine. So how do we determine these inexact numbers? Well, first, we need to have a measuring tool and knowing what base unit we are going to be measuring in. Looking at our first. So here we have a ruler. We have a line in which we want to measure. When we are doing this, we have ruler A versus ruler B. Looking at ruler B first, we want to look for what is the largest calibrated number that we can account for. Each line on these devices are calibrated. It's done by a machine to be as precise and accurate as possible. So that largest value is going to be in that place value. So here we are going to put a 2 in that 1's place. It is occupying that. Now there are no more lines between this 2 and the 3. So the observer needs to determine what's called the estimated digit. That is what makes this an inexact number, because it's going to be up to the observer what that estimated digit is. They're going to interpret where in that gray zone, in that empty area, where that measurement may fall. When you do this, so this is saying we're roughly at 2.55. So on ruler B, the that 5 that's in the 10th place, that is our estimated digit. That is what dictates the precision of the device we are working with. With the one above, however, we still have that largest calibrated mark at that 2. So we still have that 2 in that place. However, if you notice, there are more lines in between 2 and 3. And so each of those lines are still calibrated. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 lines in between the two. So that means the next one is going to be the 10th place. That is also going to be calibrated because we have a line for it. So if I go through and count 1, 2, 3, 4, 5, we for sure know that this line is past that 5th smaller calibrated mark. So we're going to put a 5 in that 10th place. So it's not to that 6 yet, so it's between this 5 and 6. Here's that estimated digit. It is up to the interpreter to figure out where this line falls. That will then occupy the next place value, and that is now becoming our estimated digit. Now notice that the first, or ruler B, occupies the estimated digit occupies the ones place, whereas in ruler A, it occupies the 100th place. Therefore, ruler A is more precise than ruler B. It collects a value that has more places occupied than ruler B can. The same thing can be said for a graduated cylinder. So here we're measuring volume. All right, so when we are looking here, what we need to do is we are going to identify what is that largest calibrated mark. We have 40 and 50. So we know the 10th place is going to be occupied, and it's not quite to the 50, so I'm going to put a 4 in the 10th place. We can see that there are lines in between the 40 and 50, and there are going to be 10 of them. That means the ones place is also occupied or known. And so we're going to have 41, 42, 43. So at the 43, not the 44, so we're going to have 43. Those are known places. But what is in between the 43 and 44? That is our estimated digit. So it's going to occupy the next place value over. We have to measure the bottom of the meniscus, so the bottom of that curve. And the bottom of that meniscus happens to fall right at that 43 line. So I interpret it to be a 0. Could someone else interpret it to be a 1? Could someone else interpret it to be 42.9? Yes, they can, because this last digit is estimated by the observer. Once we understand the precision of the device in which we are using, we can identify the number of significant figures that that number has. Now, you're not always going to be using a measuring device. You're going to have problems where you're going to be performing a calculation from a word problem. So somebody else used the measuring device. You still need to interpret the precision of the device in which they used. Therefore, you need to know what digits, what numbers can be considered significant. First rule, any non-zero. So any number between 1 and 9 are significant. Therefore, if we have the number 46, both numbers are between 1 and 9, so 4 and 6. That means we have 2 significant figures in this value. Those are easy. It's the zeros that get tricky. So we have significant zeros and we have insignificant zeros. Talking about the significant ones first. To have a zero that is significant, it needs to fall under one of these categories. First, internal zeros. Sometimes they can be called sandwiched zeros. So like 3, 0, 9. We know that the 3 and the 9 are significant. The 0 is what we call a placeholder. It is allowing the 3 to be in the hundreds place. Without that 0, that 3 would be in the tens, and that is not the same value. Therefore, that 0 is significant because it allows the 3 to occupy the place value it needs to be in. So we have 3 significant figures. Next tends to be the trickier one for most people. We have to look at the decimal point. If there is a decimal point with trailing zeros, so we have 200 decimal. That decimal tells us the precision of the device. That device tells us that we can estimate to the ones place. There is a mark for the hundreds place. There is a mark for the tens place. We estimated the ones place because that ones place has to be significant based off that zone of uncertainty that the observer noticed. We have to place a decimal. So if that line was at exactly 200, or the 2 at the 0, and we interpreted the 0, we have to put a decimal. Those 2 zeros are placeholders. They put the 2 in the appropriate place value of 100. But because this is a measured value, those zeros are significant. So with that trailing, that decimal value, these are, we would say, have 3 significant figures because we have 3 values that have to be in those placeholders. If we had 15.0, same concept. We had a measuring device that had a line for the tens, a line for the ones. The estimated digit fell to the tenths. If we interpreted that as the 1 or as a 0, that 0 is still significant. It is measured. So we still have 3 significant digits. The other one is measured 0. So if we measure something, especially temperatures where this falls, is the temperature is 0.0, those zeros are significant because they measured temperature at 0 degrees Celsius, whatever those happen to be. Insignificant zeros. Leading zeros are never significant. So these are for numbers smaller than 1. So if we have 0.01, these zeros that are preceding our first significant digit are not significant because they're just placeholders. They're putting the first significant digit in the place value it needs to reside. Therefore, this has 1 sig fig. That means the device we're using had allowed us to measure 2 just to that hundredths place. All right, so please note, zeros always put the value in the significant figure in the place value it needs to be in. However, at this point, we've always started counting with the significant digit first. But when we get to the leading zeros, the significant digit comes after the zeros. So those zeros cannot be significant. You cannot count significant figures until you reach a number between 1 and 9. If there's no decimal point with a trailing 0, so if we had that 200 but no decimal point, those zeros are not significant. They're just there to tell us that the hundredths place is occupied. So this is 1 sig fig, which means our device could only tell us roughly 200. There's no other marks. We had to do a straight up estimate. We had to estimate that hundredths place. Therefore, the zeros just put that significant figure into the hundreds. Now, typically, we will use scientific notation to ID significant figures, especially when the number gets too large or too small, or you're dealing with zeros. Any value within that scientific notation is significant, which we'll talk about in another video.